Hello Gators, this is 7.3 Sketching Slope Fields and 7.4 Reasoning Using Slope Fields. Let's take a look at this family of functions that describes the differential equation dy dx equals cosine x. So if I were to solve this, dy dx is equal to cosine x, then y would be equal to sine x plus c, where c can be represent the constant for any point that we put in it. So you can see this looks like cosine curves right here, a family of cosine curves. I want you to look at this next graph, and there's little tangents at designated x values here. And then we're going to take away the sine curve and just leave the tangent lines. Now you can see the tangent lines give an idea of what the solution looks like, and that's what this lesson is all about. Let's go ahead and take a look at this differential equation. Again, if we go ahead and solve it and find the antiderivative, will represent the solution, the family of antiderivatives. So this represents parabolas, and at different places with different points that we've been using. So that's what a slope field gives you, the idea what the solution looks like. Okay, I'd like to have you create a slope field. Creating a slope field will help you understand what a slope field does. So let's first go ahead and we're going to put little tangent lines on all of these points. Let's start with x equal to 0. So we're going to actually look at all of these points. 0, 2, 0, 1, 0, 0, 0, negative 1, 0, negative 2. All of these. We're going to take the x and y values and we're going to multiply them. And in each case, the answer will be 0. So our little tangent line will be a horizontal line. So I'm going to draw a little horizontal line. And this will be true when y is equal to 0 as well. When y is equal to 0, it doesn't matter what x is, the product will be 0. So all of these will be 0 as well. Now I'm going to take a look at something like where x is equal to 1, like this point, the point 1, 2. And when you multiply 1 and 2, which is what the differential equation wants us to do, the answer is 2. So I'm going to make a slope that has a slope of 2. So think about a slope of 2, down 2, down over 1. So this point and this point, think about making a slope that will intersect this point eventually. And then over here, we're going to have a slope of 1. And so that's up 1 over 1. Think about this point and this point, joining them. So that's a slope of 1. Over here, this will be a slope of negative 1. Think of up 1 over to the left 1. Think about lining up that. And then negative 2 over 1 up. So think about like this. So that's how we go ahead and draw those slope fields on it. And then on the next slide, I will have drawn them all using this technique. Let's go ahead and do it again. One more time. I'm going to pick 0, x equal to 0. So I'm going to pick these points, x equal to 0. When x is equal to 0, this portion will be 0, and whatever y is, that's what the slope will be. It'll be the y value. So over here at 2, this is a slope of 2, down 2 over 1. Again, try to line up this one. This is going to be a slope of 1, down 1 over 1. And then this is going to be a slope of 0, slope of negative 1, try to line those up. And then over here, over 1 up 2, slightly taller. And so what we're doing is we're getting the 2 points and putting them into the formula so that you can find. Let's do negative 1, 2. That'll yield a positive 4, which I'm going to go 1, 2, 3, 4 over 1. So I'm visualizing that like this. And visualizing 3, that will be less steep, 1, 2, 3 over 1. So that'll be less steep. Then a 2, down 2 over 1. And then a slope of 1. And then a slope of 0. All right, and then the next slide shows all of the slopes together. Okay, the figure shows the slope field. So this is the slope field. We don't have to actually do it and create all of those little tangent lines. But the question asks us to write the equation for the tangent line to this curve through this point. So we do have the point. And to do a tangent line, you also need a slope. So we want to find the slope at the point -1, -2, which means everywhere I see an x, I'm going to write -1. Wherever I see a y, I'm going to write -2. This is going to be equal to 1 minus 2 or -1. So now I know the slope. So this will be y take away a -2 equals -1 times x take away a -1. If I want to clean it up, this will be the equation of the tangent line. And if I want to kind of draw it in here, remember over here at -1, -2, right here at this point, my slope will be -1, down 1 over 1, so it will look something like this. This will be the tangent line, where it's located and what it looks like. Let's go ahead and look at this slope field and decide if we can figure out which differential equation this represents. And this is a task, so we'll work more in class, but I will help you out right now. What I'm noticing right here is I'm noticing that these slopes are 0. And these slopes are 0 at, looks like, -3, -3, -3, +3, and it looks like -2, +2, -1, +1, and it looks like at 0, -1. So it looks like all of these points I'm getting a slope. Oh, wait a minute, this slope right here is at 0 here, right here. Right here, there's a slope of 0 right here. So I want to find one of these where if I put these points in, I will get a 0 out. And you can see you're not going to get, if you put -3 in here, you're not going to get a 0 here. If you put -2 in here, you're not going to get a 0 here. But if you put -3 and 3 here, you are going to get a 0. So that looks good. This one won't work and this one won't work. So by looking at a particular slope and where it was located in the points, I can find which points are going to yield that slope of 0. So this is the correct answer. Let's go ahead and continue reasoning using slope fields. This is the slope field, and what I'd like to do is sketch the solution at 0, 2. So here is 0, 2, and we're going to let the slope field kind of be like a current in water, and we're going to let it help us take us to the next step. So over here at 0, 2, the slope field is taking us just like a current, like this. And then we're going to follow down until we get over here. Let me change color and let me do it at -1, -2, -1, -2. And again, I'm going to follow it like a current, following it like a current, and then going over here and following it like a water current here. Now, there do exist programs that will help you do this. And let me go ahead and show you a GeoGebra one. And you can see this is the graph that we just were working with. And 0, 2, the computer actually figures it out, and look at, it's just following the tangent lines just like a current. And over here at -1, -2, again, following the tangent lines. So there are programs that will do this for you. Let's now take a look at this slope field and see if we can figure out, with this initial condition, which one of these might be the solution. These are not differential equations, these are solutions. I know the point 0, 0 must work here, and I can already tell that the point 0, 0 does not work here. If I were to put 0 right in here, this would be e squared, and e squared is not 0. So this solution does not have 0, 0, so that won't work. All of these solutions have a denominator, and each one of these denominators, remember, 2 plus x cannot equal 0. So that tells me at x equal to -2, we have a vertical asymptote, which is, look at like what is happening here. We have a vertical asymptote here. This will have a vertical asymptote at -2, and this one is x plus 2 and x minus 2. This one will have 2 vertical asymptotes, and since I don't have a vertical asymptote at 2, I can cross this one out. And I think I will cross this one out because tangent, remember has an asymptotic behavior. Remember, tangent looks like this. Every time cosine is 0, there will be asymptotes. So there would be a lot more in this one with tangent in the numerator. So it looks like matter of elimination. This is the answer. Let's now consider this slope field and describe all points for which the derivative is equal to -1. Okay, derivative equal to -1. All of these tangents right here are equal to -1. Looks like they're right around here. And can we describe all of these points where they're located? We can. We can take the differential equation, which is dy dx equal to x plus 1 over y. And we know that this part is -1. And then we're going to multiply both sides by y. So this is opposite of y is equal to x plus 1. And then y, I'm going to multiply everything through by -1. Negative x minus 1. And that series of points looks like this. So all the points that have a slope of -1 are located right here. These are where all the points are located. And so we would say all points where dy dx equals -1 are located at y equals -x minus 1. So in this range right here, y equal to -x minus 1. Okay, let's explain why this is not the slope field for this. All right, now it looks like the slope field relies only on the y coordinate. And when it relies only on the y coordinate, that means, like, say if y is equal to 3, then just putting the number 3, so dy dt when y is equal to 3 will be equal to -0.9. That means it doesn't matter what the x is, as long as y is equal to 3. Now look at all of these points right here. All of these points have the same thing, y is equal to 3, yet every single one of them don't look like they're the same. They don't look like they're -0.9. So that's why this picture does not represent this differential equation. And there's different ways you could write the answer, and here is one way. You could say one possible answer is when y is equal to 0, when y is equal to 0 right here, the slopes of the line segments y equal to 0 are non-zero. You can see they are not equal to 0.